So, continuing through in the realm of matrices, looking at the determinants, inverses, and transposes of a matrix. The transpose of a matrix, which is given as A superscript T or A prime or A dash if you'd prefer, is obtained by swapping the rows with the columns. So if we have A is equal to that matrix there, then AT or A prime is equal to So we can see the row 2, negative 4, 5 has become a column, 2, negative 4, 5, and negative 1, 3, 8 has become a column as well. So if we have a square matrix, we can find an interesting property known as the determinant. And basically the determinant tells us, is a number able to be inverted? So can we find a multiplicative inverse that when multiplied by the matrix gives us the identity matrix? But let's not get too ahead of ourselves. So it's written as det A or delta or A with a like absolute values around it. It's a single number associated for the matrix. And so for A equals ABCD, it is simply A times D, take B times C. So the product of the main diagonal with the other diagonal. So for the matrix B, let's calculate the determinant of B and then B transpose. So for our first example, we get 3 times 7, take 5 times 4, which is just equal to 1. And for our second example, instead of taking it of that, we're now taking it of 3, 5, 4, 7. We still get 3 times 7, and we still get 5 times 4. So we get the exact same determinant. So we can see that for any square matrix, the determinant of A is equal to the determinant of A transpose. So we can then use this determinant to find what's called the inverse of a 2 by 2 matrix. This is what I was just talking about before. So for a square matrix A, the multiplicative inverse is called the inverse matrix, denoted by A to the negative 1. When A is multiplied by A to the negative 1, the identity matrix I is obtained, i.e. A inverse is equal to A inverse A, which is equal to I. Now note, A inverse is not the same as 1 over A. Division of matrices is not defined. If we try to divide 1 by a matrix, it's not something that can be done. So instead of dividing by a number, we multiply by its inverse, which is kind of the same as what we do in regular arithmetic. Like if I were to say 3 divided by 3 is equal to 1, which is our identity for just regular numbers, that's the same as 3 times 3 to the negative 1. So it's just sort of a change of notation because division isn't something we can do, but we can multiply by inverses. So determine the inverse of B and verify that B inverse is equal to B inverse B is equal to the identity. So but before I get too ahead of myself, I should give you the formula for finding it. So for A equal to ABCD, we get A inverse is just 1 over the determinant. And then we swap the main diagonal, so it becomes DA, and we change the sign of our other diagonal. So D, negative B, negative C, A. So in our case here, we first need to find the determinant. So the determinant of our number is 1 over AD take BC. So we're trying to find the inverse of this. Let's just write out our formula. And so that is going to give us 1 over 10 take negative 3, being multiplied by 5, negative 3, 1, 2. So we've swapped that main diagonal, and so all we get is 1/13 of 5, negative 3, 1, and 2. So if I were to test this, B inverse B is equal to 1/13 of 5, negative 3, 1, 2, multiplied by 2, 3, negative 1, 5. And what we see here is we get 5 times 2 is 10. Negative 3 times negative 1 is positive 3, so that gives us 13. We get 5 times 3, take 3 times 5 is 0. 1 times 2, take 2 times 1 is 0. And then 1 times 3 plus 2 times 5 is 13. So we can see this is just the identity matrix, as expected. Let's make sure it works the other way and that it isn't just a fluke. Okay, so when it comes to multiplying by scalars, we can actually take this guy out the front and multiply him as the last step. So this becomes 1/13 times the product of the other two. Okay, because multiplying by scalars is still commutative, we don't need to worry about the order of that. It's just the order of the matrix multiplication we care about. And so what we get is 1/13 of 2 times, hey, these are the same sums that we were just looking at. So this becomes 13, 0, 0, 13. You can check that if you don't believe me. And so that is also the identity. So we see that no matter which way we multiply the inverse and the original, we get the identity. All right, last thing that we're going to look at for this video is an idea of singular matrices. So a matrix is singular if it has no inverse. And you might be thinking, no inverse? Well, how can it have no inverse? Every number that we know of has an inverse. I can divide anything, but can you? There's one number that comes to mind that has no multiplicative inverse in regular numbers, and it's 0. So we don't know what division by 0 is. It doesn't exist. And that property also applies to the inverse of our matrices. So if the determinant is equal to 0, then this 13, this denominator up in that previous example, that's going to be 0, and that's not defined. It's not something that we have a definition for. So no inverse can exist. So if we're asked to find, for example 9, determine the values of x if the matrix is singular, well, we're looking where is the determinant 0. So singular if the determinant of A is equal to 0. So we get A times D, take B times C is equal to 0. And so that gives us x take 3, x plus 2, take 6. Right, x take 3. Is equal to 0. So if we expand and group like terms, we get x squared minus x minus 12 is equal to 0. So we're looking for two numbers that multiply together to make negative 12 and add together to make negative 1. So x take 4 and x plus 3 fit the job there. And so that means that x equals 4. Sorry, I shouldn't say and, I should say or. X equals negative 3. And so we can see that the two matrices that we have here that are singular are 1, 3, 2, 6. And negative 6, 3, 2, negative 1. And we can actually test this just by looking at it. If I were to multiply the main diagonal, I'd get 6. Subtract the opposite diagonal, well, that's going to be 6 take 6. That doesn't exist. Well, sorry, it does exist. It's 0, but then 1 over it doesn't exist. And same thing for this. Negative 6 times negative 1 is positive 6, take 6 is also 0. So both of these matrices are what we call singular. They have no inverse. And that's all for this video. Thank you very much for watching.